Hello, everyone. Thank you for joining today's John Bacall Colloquium. I'm Jared Heist, the Director of Science here at SURF. A few quick housekeeping notes before we begin. Today's talk will be about 45 minutes, followed by 10 to 15 minutes of Q&A.
Thank you for joining today's John Bacall Colloquium.
You can ask questions live by raising your hand in Zoom or by using the Q&A button. This talk is being recorded and will be available on institute.surf/JBC, as well as on SURF's YouTube and Vimeo channels. To receive notifications about upcoming talks, visit the Connect link at the top of the institute.surf webpage. You can register for all scheduled talks at institute.surf/JBC. We now have a dedicated Slack channel to continue the conversation after each colloquium or to follow up later. A link to the Slack channel is in the Zoom chat. You're welcome to ask additional questions of the speaker or engage the broader group assembled there. The featured speaker will be available on Slack for up to about 30 minutes following the talk. Now it's my pleasure to introduce today's speaker. Dr. Sunny So is a senior scientist at Fermilab, where she works on two pioneering neutrino experiments: the Deep Underground Neutrino Experiment DUNE, a flagship international project, and the ICARUS Short Baseline Neutrino Program. Dr. So earned her PhD from the University of Minnesota in 2004, studying subatomic particles, charmonium, in the E835 fixed target experiment at Fermilab. Since then, she has devoted 2 decades to experimental neutrino physics, contributing to major international collaborations, including IceCube, Reno, Hyperkamiokande, and the proposed long baseline experiment with a site in Korea, T to HKK, NEOS-2, and neutrino oscillations study using a liquid scintillator target. Her career has spanned institutions across 3 continents, including time at Penn State University, Stockholm University, and Seoul National University, and the Institute for Basic Science in South Korea. Dr. So's research explores fundamental questions about the universe through neutrino oscillations, sterile neutrinos, and signals from reactors, the sun, and supernovae. She also investigates physics beyond the standard model and has recently integrated AI and machine learning into her work. Dr. So's contributions to the field have earned international recognition. In 2018, she received the inaugural Women Scientist Award from France Korea Particle Physics Laboratory. She's been a member of the International Neutrino Commission since 2022 and served on the International Union of Pure and Applied Physics in astroparticle physics from 2017 to 2024, representing South Korea. Most recently, she served on the P5, the Particle Physics Project Prioritization Panel, which shapes the long-term strategic direction of U.S. particle physics research. With that introduction, let's get ready to learn about DUNE, a new era for neutrino discovery.
Okay, good morning. Thank you for a nice introduction, Jared. It's a special privilege to speak at the John Bacall Colloquium at SURF. My talk today is about DUNE, succeeding Bacall's legacy for new discovery. So let's start with the Bacall legacy, where the story begins and it continues. So John Bacall spent decades to calculate solar neutrino flux, and the outcome is standard solar model. And this plot is the visualization of his model. And it shows solar neutrino flux in the y-axis as a function of neutrino energy. However, his solar neutrino model has been challenged by experiments, and Ray Davis was the first one who tried to confirm Bacall's solar model. And so he built a tank of cleaning fluid in Homestead Gold Mine in Lead in South Dakota, where current SURF is. And Ray and his team observed only 1/3 of predicted solar neutrinos. So this discrepancy between experiment and the model is called solar neutrino problem. And this problem has been there for 3 decades. And the answer came in 1998 by Super Kamiokande experiment and 2001 by Snow experiment. The key is neutrino oscillation. So neutrinos, they change their flavors when they propagate. So depending on where you detect neutrinos, you can measure different ratio of neutrino flavors. And that's neutrino oscillation. So even though sun produces electron-type neutrinos, through the long distance, the electron neutrino can oscillate or convert to other types of neutrino, depending on where they are produced. And at the Earth, we see all 3 flavors of neutrinos. So there was no real solar neutrino problem. Both John Bacall and Ray Davis, they were correct. So what causes neutrino oscillation? We need 2 conditions. The first is the flavor state of neutrinos, nu-e, nu-mu, and nu-tau, is not the same as mass states, nu-1, nu-2, nu-3. And the second condition is that all 3 neutrino masses are not equal. So you need these 2 conditions. And the 2 states can be connected by a unitary matrix called PMNS matrix. The name is coming from the 4th theorist's name. And it has 3 neutrino mixing angles, zeta 1, 2, zeta 2, 3, zeta 1, 3. And 2 mass square difference, delta m squared 2, 1, and delta m squared 3, 1. So all these 3 angles and mass square differences are relatively well measured. But we still don't know what's the sign of delta m squared 3, 1. Is it positive or negative? If it's positive, we call it normal mass ordering. It's negative, it's inverted mass ordering. And we still don't know also this CP violation phase delta CP in the PMNS matrix. And these 2 measurements are really the flagship measurement in today's neutrino physics. And DUNE and Hyper-K are designed to measure these 2 parameters precisely. So where the field stands today. So this is a short summary of recent neutrino news. So KM3net, ARCA, they observed highest energy neutrinos from astrophysical source. And the energy is 220 PeV. This is 10 to the 15 electron volt. And Catherine set an upper limit for neutrino mass, that is less than 0.45 electron volt at 90% confidence level. And Microboon excluded EV scale stellar neutrinos in 3+1 model at 95% confidence level. And NOVA preferred normal mass ordering, but the significance is very low. So that's the reason why we need DUNE. So NOVA and T2K published joint fit analysis last year in Nature, and this plot shows CP violation phase in the x-axis. In the y-axis is sine square zeta 2, 3. So inverted ordering case, NOVA T2K, they agree well. So T2K is red and NOVA is blue. And in the normal ordering case, as you can see here, T2K preferred reason and NOVA preferred reason in blue. They don't overlap. They prefer different reasons, but they have huge uncertainty. So this is the reason why we need DUNE again. And NOVA T2K joint fit for delta m squared 3.2 measurement is currently world best, and it's about 1.4% level. So what it takes to resolve mass ordering and delta CP? So first, we need strong matter effects, and this will separate mass ordering from CP violation. And for this, we need a long baseline, and DUNE has 1,300 kilometer baseline. And we need also broad spectral coverage, and this will break additional parameter degeneracies. And with this broad spectrum, we can cover first and second oscillation maximum. So DUNE actually has wideband beam from 0.5 to 7 GeV. And third, we need a good control of flux, neutrino flux, and cross-section uncertainty. And DUNE has a multi-technology near detector complex, and it can really control the systematics very well for mass ordering delta CP measurement. And we also need high-resolution imaging to identify electron neutrinos from muon neutrino background. And liquid argon TPC is the right technology for this. And we also need high statistics for precise measurement. And DUNE will have more than 2 megawatt beam with a 40 kiloton detector. So DUNE is really designed to answer with long baseline neutrino facility, LBNF, and DUNE detectors. So this shows the DUNE collaboration photo taken about a year ago at Fermilab. And DUNE has more than 1,500 collaborators from more than 220 institutions from 37 countries plus CERN. And this orange color shows the DUNE collaborators in the map. So DUNE is the largest neutrino collaboration in history. So this cartoon shows the DUNE experiment. So Fermilab will produce high intensity beam greater than 2 megawatt in 2 phases. And so muon neutrino is produced and it's sent to the FAR detector at SURF. So the baseline is 1,300 kilometer. And underground SURF, we will have 4 modules of liquid argon TPC or equivalent TPC detector. And we have near detector complex at Fermilab. The baseline is 562 meter. So in phase 1, neutrino beam production, we target for 1.2 megawatt. And thanks to the new LINAC called PIP2, PIP2 means Proton Improvement Plan, that uses superconducting RF cavity here. So it will accelerate H- ion up to 800 MeV and send it to booster. So the 2 electrons from hydrogen ion is stripped off, and then it's accelerated to HeV, and then it enters to main injector, and the proton gets energy up to 120 GeV, and then it sends to the target. So this is the target area. So we use a graphite target for this. And mesons, including pions, kaons, are produced, and those mesons decay here in the decay pipe, less than 200 meters, and neutrinos are produced. And we have observer here to filter out all standard model particles except neutrinos. So muon neutrino only exits here. Near detector position is here. So Fermilab produces wideband beam, and it has clear benefits. And this plot shows nu mu to nu e appearance probability. And the solid line shows the oscillation probability for different delta CP values and mass ordering. And this is the nu mu flux on oscillated neutrino flux. So first oscillation maximum is happening around 2.4 GeV at FAR detector, and second oscillation maximum is 0.8 GeV. So by having this wideband beam, we can really cover 2 oscillation maxima that enables a simultaneous fit of delta CP, mass ordering, and zeta 2-3. And it preserves full L over E spectral structure. So that enables delta CP violation from matter effects distinction. Because these 2 parameters, they depend, they have different energy dependency. And LAR TPC really suits well for, wideband beam, unlike, water Cherenkov detector. So LAR TPC is a particle camera. It's a really imaging detector, 3D imaging. So for TPC, we need cathode, anode, and electric field. So when neutrino enters to liquid argon TPC, it interacts with the liquid argon and produces secondary particles. So secondary particles, they lose energy by ionizing argon atom, and electrons are produced. And those electrons drift towards anode. In anode, we have 3 planes, and 2 planes, first 2 planes are induction plane, and the last plane is collection plane. So drift electrons just pass induction layer, so it leaves these bipolar signals. In collection plane, it just captured, so it gives us only a single unipolar signal. So LAR-TPC is really good for particle identification and vertex resolution, and it's a good calorimetry which can access low energy threshold. So this is the real event display taken from ProtoDune. Charged pion beam, 6 GeV charged pion beam enters and interact with liquid argon producing proton, and 3 charged pions and 2 photons. And there is a cosmic muon, it's shown here. So phase 1, we have 2 far detectors at surf, and one type is horizontal drift, the other type is vertical drift. So in horizontal drift, we have 2 cathodes, and each cathode have 2 anodes. So that horizontal drift, we have 4 TPC regions, and drift distance is 3.6 meter. While in the vertical drift, we have only 1 cathode and 2 anodes planes, so that drift distance is longer, 6.25 meter. And the 2 far detectors use different anode system. The horizontal drift use wire readout, which I introduced earlier. It's called anode plane assembly. Vertical drift case, it uses conductive strip instead of wires on printed circuit board, and we call it charge readout plane. Both far detector modules have photon detectors called XR-PUCA. So let me introduce XR-PUCA. So these are the real photos of XR-PUCA. Left is for vertical drift and right top is horizontal drift. They have different size and different configurations. So XR-PUCA means photon trap in Brazilian world or South American world. And actually it traps the light. So scintillation light produced in the liquid argon from the particle interaction, they enter this XR-PUCA. But the scintillation light wavelength in liquid argon is 128 nanometers, so it cannot be directly, detected by PMTs or SIPM. So this XR-PUCA system shifts the wavelengths which can be accepted by the SIPM. So when it passes PTP, this 128 nanometer shifts to 350 nanometer, and this wavelengths can pass dichroic filter. And when it hits the wavelength shift, this is further shifted to 430 nanometer. So we can reflect here, but it cannot pass dichroic filter because 430 nanometer is above the threshold of dichroic filter, so it cannot pass. So this is entrance IPM detected. So once you have this, light in, it just, never escapes. So that's why it's called photon trap. So near detector complex, we have 3 types of detectors, and this is the beam direction. The first detector is ND-LAR. This uses the same technology as far detector use. The muon spectrometer, it measures muon momentum and charge from the escaping muons from ND-LAR. And we have SAND detector, which is a magnetized calorimeter and tracker. It monitors neutrino flux. And this detector just sits there, fixed. While ND-LAR and TMS detector, they can be moved from the beam axis, central axis. So maximum distance it can move is less than 30 meters. So there's a reason for doing this, moving the detector, because on axis, we observe only, this on axis flux. By moving these 2 detectors, measures fluxes at different distances, we can measure this more narrower neutrinos with lower energy. So this system, we call it PRISM, and this is essential to really reduce the systematic uncertainties for oscillation physics for far detector, but near detector also can do interesting physics for cross-section measurement and new physics searches. So NDLR case, unlike far detector is pretty modularized, and 7.5 arrays, total 35 modules. And there is a reason for making this modular detector. It's intentional. Because near detector, we have many neutrinos. Thanks to the high intensity beam and also the close distance, we expect multiple neutrino interactions per one readout time. So if we have only one just single bulk detector here, we will have ambiguities from the multiple neutrino interactions. So that having this modular detector, we can really, reduce the ambiguities. And each module has 2 TPCs by having one cathode, and the drift distance is 50 centimeter. And each module is also optically, isolated. And unlike far detector, near detector has a pixel detector. And this is more advanced technology, and we can call this is truly 3D. With wire or strip detector, it's a little bit more ambiguous, but this one is, we can measure particle interaction positions and trajectories precisely with less ambiguity. So what DUNE will discover and measure? And this slide shows the DUNE science. So we can do neutrino oscillation physics and neutrino cross-section measurement with beam. But no matter what we have beam or not, we can always measure atmospheric neutrinos and supernova burst neutrinos and solar neutrinos. And DUNE is the great place for new physics searches. So DUNE is quite unique since it can measure all PMNS parameters in one experiment. And this will reduce systematic uncertainties. And we measure first and second oscillation maxima. This resolves degeneracy of the parameters. And DUNE can measure mass ordering greater than 5 sigma with a single detector alone. And DUNE can measure non-standard neutrino interaction in world best. So this plot shows oscillated nu-E appearance spectra at far detector. Left is nu-E, right is nu-E bar antineutrino. And there are many lines here, but the red represent normal ordering and blue is inverted ordering, the same for here. And solid line is delta Cp is minus pi over 2. Dotted line is delta Cp pi over 2. So thanks to the Earth's matter effect, the mass ordering is really clearly distinguished, as you can see here. Normal ordering, red, these two, within this delta Cp coverage, versus inverted ordering. So basically, no matter what delta Cp value is, we can clearly distinguish mass ordering. The opposite is true for nu-E bar. This normal ordering is suppressed, but inverted ordering is more enhanced, amplified. So we can do mass ordering determination in few years, not decades. So this plot shows neutrino mass ordering sensitivity as a function of DUNE operation time. So best case scenario, that is delta Cp is equal to minus pi over 2, we can determine mass ordering greater than 5 sigma in 1 year. Worst case scenario, if we don't know, delta Cp, we can still determine mass ordering greater than 5 sigma in about 3 years. So now Cp violation in nu-E and nu-E bar events. So these two plots I showed you, and by counting nu-E events and nu-E bar events for a given mass ordering and given delta Cp, we can draw this plot. Okay, so the blue is inverted ordering and red is normal ordering. And these ellipses represent different values of delta Cp. Okay, so this really shows that, DUNE can distinguish mass ordering, inverted and normal ordering very well because they are well separated. And also this ellipse is, degeneracy is really broken so that we can measure CP violation phase well. Compared to hyper-K, hyper-K inverted ordering, normal ordering, they overlaps. And also this ellipse is really shrinked. So it's highly degenerated. So that means it's difficult to measure. So CP violation sensitivity plot is shown here. So as a function of data taking time, so we can discover delta CP at 5 sigma if delta CP is minus pi over 2. So it takes about 7 years. We can also cover 75% of delta CP region, allowed region, at 3 sigma. And it takes a bit less than 15 years. But this requires DUNE phase 2. But we don't know exactly when phase 2 can start. So this year is not really meaningful here. But, no matter what the year the phase 2 starts, we do need DUNE phase 2 to achieve our science goal. So resolving delta CP and zeta 1,3. So this plot shows delta CP resolution. That means, smaller value, the better, as a function of delta CP. So with more than 1,100 kiloton megawatt year exposure, that's the best case scenario, we can reach the resolution of 6 degree or 19 degree, depending on what true delta CP is. And DUNE is also very sensitive to zeta 1,3. So zeta 1,3 measurement, the precision is comparable to reactor experiments. Zeta 2,3 and delta M square 3,2 precision. So with 336 kiloton megawatt year data, this number shows 1 sigma uncertainty for these two parameters. And compared to current world average 1 sigma value here, DUNE can do 2 times better precision in sine square zeta 2,3, and a little bit less than 2 times better in delta M square 3,2. And I want to emphasize that DUNE is the experiment which can measure zeta 2,3 world best. And this shows the contour plot of those two parameters, and 336 exposure is shown in blue, and the world average using NUPID 4.0. This is a little bit old model, but yeah, that is shown in this yellow region. So atmospheric neutrinos. So we expect about 2,500 events per year per each module, 10 kiloton. And we can, so this is for all flavors. So atmospheric neutrinos provide extra sensitivity to delta CP and mass ordering. So delta CP sensitivity is coming from sub-GeV upcoming atmospheric neutrinos, while mass ordering is coming from pure GeV upgoing atmospheric neutrinos. And this is due to the mass resonance effects, matter effects in this region, 2 to 10 MeV region. And this plot shows actually mass ordering plot. So in this, why the color bar represent probability of nu mu to nu e with normal ordering minus probability of inverted ordering. So in this region, 2 to 10 GeV region, you see huge difference, around minus 0.4, because of this matter effects really, separates these two mass ordering. While vacuum oscillation region, you see small differences, close to, within 0.1. So it's difficult here, mass ordering. And this plot shows delta CP, power of sub-GeV outgoing atmospheric neutrinos. So you see some clear features here. And this is the probability of mu to nu e when delta CP is pi over 2 minus probability of delta CP is 0. So no CP violation. So this plot is not from DUNE, but this paper. And it shows that, DUNE light detector with 400 kiloton year exposure, DUNE can exclude CP conserving phase pi more than 3 sigma. If CP conserving delta CP is 0 or 2 pi, the sensitivity goes down less than 2 sigma. So supernova neutrinos. So core collapse supernova neutrino, we expect about 1 to 3 per century in our galaxy. So more than 99% of energy is carried out by these neutrinos, and neutrinos are emitted in all flavors. And DUNE is sensitive to electron neutrinos, while Hyper-K or Juno experiments, they are sensitive to electron antineutrinos. With these neutrinos, we can point the supernova burst to optical telescope. With 40 kiloton for 4 modules, our pointing resolution is 4.3 degree in realistic scenario. But not only the supernova pointing, we can do also astrophysics, what's the supernova burst mechanism by measuring a neutrino luminosity and energy and spectral spectrum shape parameter alpha as a function of time. And also we can determine neutrino mass ordering by measure the spectrum of these neutrinos as a function of time. So normal ordering case is red and green is the inverted ordering. Blue is the non-oscillation case. So DUNE is also sensitive to solar neutrinos. Since we have huge radiological background below 10 MeV, currently we are looking at about 10 MeV region. And here we can measure boron A solar neutrinos in this orange color. And also we can discover HEP neutrinos that is shown in red. DUNE is also sensitive to solar parameters by measuring day-night asymmetry. And this will be the complementary to Juno's solar parameter measurement. So DUNE's sensitivity is shown in this blue region. So broad BSM program. DUNE is really the playground for new physics searches. So non-standard interaction, thanks to the huge matter effects, when neutrinos propagate in matter, if there is a non-standard interaction, we will have some non-zero values of these epsilon parameters. And so our sensitivity is shown in these lines. The red one is 1 sigma and the blue is about 2 sigma level. And current bound is here. So we can do really excellent measurement. And DUNE can also do stellar neutrino search. And this plot shows. So thanks to 2 detectors, near detector and far detector, we can really constrain stellar neutrinos pretty well. And this red line shows the stellar neutrino, the disappearance due to stellar neutrinos in this particular case of stellar neutrino mass of 50 eV square. And we can do really well for inelastic boosted dark matter. Our sensitivity is shown here in the far detector. And also we are sensitive to proton decay, especially proton decay to kaon to antineutrino channel. And also neutrino trident. Trident is actually standard model process, but it's very rare. But thanks to high statistics in near detector, we can precisely measure trident signal, so then maybe we have chance for new physics. And also we have an NMR oscillation and long list of new physics program I cannot really cover here. So DUNE is an AI detector. So DOE also launched the Genesis mission last November. So DUNE is an imaging detector. So this is the perfect place for AI, using AI. So DUNE uses convolutional neural network, graph neural network, and transformers. And also recently, large language models like ChatGPT, Claude, and foundation models, agentic AIs are also actively developed for various purposes. And DUNE uses AI infrastructures, including high-performance computing and distributed computing. And DUNE has been using AI in all these areas. So let me highlight some use case of AI ML that really transforming LRTPC reconstruction. So convolutional neural network. Using this, we can achieve 90% of electron neutrino efficiency and 95% NUMU efficiency in far detector simulation. And SPINE is an end-to-end event reconstruction, and this shows the architecture of the SPINE. It's very complicated. And this shows one of the performance of the spine. This shows the semantic labeling of the pixel. And from UResNet. So Pandora Deep Learning Vertex, we can improve more than 20% for sub-centimeter vertex reconstruction. And kinematic reconstruction deep neural network, we can have about 50% improvement for nu-mu, contained nu-mu energy resolution. That is shown here. So without deep neural network, it's shown red. With DNN, it becomes blue. And about 8 times improvement for electron energy bias, it's shown here. So using this DNN, the red becomes this blue. And we have, many active R&D ongoing. So prototype detectors. So at CERN, we have Neutrino platform where we have 2 proto-DUNE detectors, proto-DUNE HD and VD, vertical drift. Each have 770 ton liquid argon. So it's about 5% of the full FAR detector size. So before proto-DUNE 2 with horizontal drift and vertical drift, we had a single phase. So data taking was in 2018 to 2020. It has been successful, and we published 13 papers, and we have more ongoing analysis. And using this data, we really tested for GEANT4 and Gini argon scattering models. And these are just 2 examples of our cross-section measurement for pi plus and proton total inelastic scattering measurement. So proto-DUNE 2, high horizontal drift, we take data in 2024 for 10 weeks. This is horizontal drift, and this is vertical drift. Data taken was done in last year for 5 weeks with beam, and data taking without beam is still ongoing. And this is the photo of proto-DUNE vertical drift and charge readout unit and XR Fukas here. And this plot shows electron lifetime in the y-axis as a function of time. So you can see our electron lifetime is, mostly above 20 milliseconds. That is well above our requirement, which is 6 milliseconds. So first near detector prototype, we call near detector LAR 2x2 because we have total 4 modules. And this module will be inserted to cryostat. And the LAR 2x2 is surrounded by Minerva tracker detectors here to measure muons escaping 2x2. So 2x2 detector took nu-mu beam data in 2024, less than 5 days of data. They collected 25,000 neutrino interactions. And later this year, we expect another nu-mu beam data taking. So this is a beautiful event display from the first neutrino beam data from nu-mu beam using 2x2 detector. And this is the full-scale demonstrator in Bern, Switzerland. And this is cosmic muon data. And this is really successful test bed for full size of near detector LAR-TBC. So milestones and progresses. So far, caverns are ready. And the cavern, construction started in excavation started in 2019 by refurbishing existing facilities. After then, drilling, blasting, and finally in 2024, cavern is completed. In 2026, we got the project of the year from the Underground Construction Association. And this just shows the cavern rock disposal area. So in this, cartoon, this is the rock disposal area. So underground laboratory, the rocks are excavated and sent up to the ground level, and they are disposed here. So this shows the layout of our underground lab. The depth is 1.5 kilometer, And DUNE first far detector module will be here, second module, third module, fourth module, and beam direction is here. This is just comparison of Homestake experiment. We have about 100 times bigger detector than Homestake mine experiments. So this shows the photos of DUNE cryostat. So DUNE cryostat actually consists of several layers, and this is the outermost layer. So DUNE far detector will be, finally, these steel beams will be attached here in this red color. So last Thursday, DUNE cryostat beam signing ceremony. So a lot of, key people visited SURF. So far detector vertical drift progress. So there is a full-scale mock test is ongoing at CERN, and this photo shows the mock test setups. And we recently finished DOE review CD2 and 3 for far detector successfully, and this means that DOE gives us budget to construct far detectors. This is a great milestone for us. Far detector horizontal drift, what's the progress? So we will need total 150 anode plane assemblies by early 2029. And early this year, 50 APAs were produced by UK, and 8 APAs were shipped to Fermilab. And this photo shows the APAs at Southampton, and finally delivered at Fermilab. And U of Chicago will also contribute about 10% of APAs. So far detector construction photos are shown here. This is APA construction. This is photon detection, Exarabuka assembly. And this is charge readout plane testing for vertical drift. And this is Exarabuka and near detector progress. So DUNE prism system testing is ongoing in Minnesota. Sand integration test was at INFM. And Louisiana State University test sand for TMS, the mu spectrometer electronics. And test cryostat arrived at Fermilab recently. So what's ahead? So this is our time schedule for DUNE phase 1. So cryostat installation starts in 2026, quarter 3, and installation completes end of 2027 when far detector installation begins. And early 2030, with far detector, we will start data taking without beam. And DUNE beams will be delivered in 2031. And 2032, ND detector will be ready. So during the phase 1 operation, we will transition to phase 2. So phase 2 is really completing our vision. It's not expanding our vision, it's the completing the vision. So by having far detector third module, we will apply some more advanced RTPS technologies. And module 4, we call it module of opportunity. So several different types of R&Ds are being developed for this module 4. And MDGAR will replace the muon spectrometer, and it is a high pressure gaseous argon TPC. And we expect this will further reduce systematic uncertainty for oscillation analysis and beam upgrade up to greater than 2 megawatt. So DUNE phase 2 really targets for delta CP coverage 75% at 3 sigma or 50% at 5 sigma. So full oscillation precision is possible with DUNE phase 2, and we can enhance low energy physics and BSM program. So this plot clearly shows why DUNE needs phase 2. Okay, so with phase 1 and phase 2. With phase 1, we will never reach 5 sigma. Okay, so summary and conclusion. So open questions demand DUNE, and DUNE is unique and multi-purpose. AI is growing in, and improving DUNE. Prototype detectors have been successful. Carbon at surface is ready. Neutrino beamline at Fermilab is progressing. Detector construction is going well. First non-beam data in early 2030 at SURF, and first beam delivery in 2031. And near detector data taking hopefully in 2032. And DUNE phase 2 R&D is going well. So DUNE represent crucial next steps in the mission started by Bakar. So this is the Bakar and Ray Davis lab, and now it's home to DUNE. So thank you so much for your attention.
Thank you, Dr. So. That was a wonderful survey of all the great science we're expecting from DUNE. We're super excited about hosting DUNE, and we're looking very much forward to that science. Let's see if there are any questions from our audience here. While we're waiting, why don't I tee one up? You mentioned the Genesis mission and the funding for that important program within the Department of Energy. Can you say a bit more about how AI might help improve sensitivity to low energy, such as solar neutrinos or possibly even supernova neutrino signals?
Yeah, so I mean, in general, machine learning really, can do better than, human, right? So it has been demonstrated. That is also true for low energy physics. And currently, some activities ongoing to apply, machine learning to improve such low energy events detection, to improve efficiency and also improve the purity. And so I don't know how to answer for your question because machine learning, human has real limitation, right? Machine learning, it can see multiple dimensions. It really extracts the features from the event. Okay, and so basically it does better than human being, and so I don't know how else I can explain it better. And supernova pointing is one of the places they try to use machine learning, and so that especially pointing case, we need fast reconstruction of the pointing for a given time, and it's still ongoing. So we will see how much we can improve.
Very good. Let's see, any questions from the audience? Feel free to put them in the Q&A or raise your hand, and we can unmute you to ask your questions live. Maybe one more question. You mentioned the phase 2, of course, to extend the reach of the DUNE science program to cover all of the main science goals that have been laid out this P5 and the P5 before it. So we're keeping on that strategy. You had a high level summary of some of the upgrades for a phase 2 FAR detector. Can you just say a few more words about that?
Okay, so yeah. So FAR detector, phase 2 is FD3. So we will have some, improved light collection using something called Apex, and it uses AIs. And also, for higher signal yield for low energy physics is expected because this Apex really, covers entire world of the FAR detector. And FAR detector 4 is a model of opportunity. So actually for this one, maybe I can show, So a lot of, R&Ds are ongoing. So we have two types of signals, ionized electrons and scintillation light. So for electron signal case, we have, three types of R&Ds ongoing for pixel readout. So one is light pix that is currently being used in ND2x2 and will be used in near detector. And there's also QPIX, similar technology, but with a little bit different way, and also GANPIX. And here, so this plot shows some scheme. So this is LARPIX, and this is showing GANPIX. Actually this is aiming for low energy physics. And actually GANPIX is having both pixel and photon detectors. So that actually, sorry, this is actually not GANPIX. This I'm a little bit myself is confused. This is actually the system where we can have both electron detection and light detection in the same module together, solar, charge and light, integrated. Okay, and also we have also another technology called Ariadne that converts electrons to photons using this THGEM technology, and it uses really the cameras to detect these photons. And for scintillation light, it produces photon. We have LightPix R&D and QPix LILA R&D is ongoing. So this itself is one talk. So more details can be found in this white paper.
Very good, thank you. There's a question in the chat. Maybe I'll just quickly summarize it here. Talking about backgrounds, liquid argon has a small amount of radioactive argon-42. Any plans on how DUNE is going to mitigate that background?
So actually, we have lots of radiological background. So there is some efforts ongoing to reduce these backgrounds by having some passive shieldings, but then needs approval from the collaboration. So but let's see the solar neutrinos case again. So it will really reduce having shielding, passive shielding. We can access lower energy, but we still have huge neutrons. Neutrons are difficult to reduce, but having some passive shieldings like water or polyethylene, we can reduce this neutron background. And also in high energy, the external gammas are also another main background. So there's a big efforts ongoing, including University of South Dakota mines. That is one of the leading place for this effort. So we will see. The study is not finalized yet.
I think one of the phase 2, maybe even the modular opportunity, is also considering underground argon for mitigating some of these backgrounds. Maybe one more question here for Mike Ray. Question to you, Dr. Seo. What is the most exciting potential findings in the first few years of DUNE experiment operation? And what are you most excited to be looking for in that period of time?
Yes, that's a very good question. And first couple of years, if we have a beam, we can determine neutrino mass ordering with more than 5 sigma within 3 years, no matter what the delta Cp value is. But while we are waiting for the DUNE beam is coming, we can do other physics. So one place would be VSM search, VSM physics search. We can do I have shown you the sensitivities already. Where did I show? So this sensitivity is possible without beam. And this is actually assuming 300 kiloton year. No, this is hypothetical. So this is 40 kiloton year. So and also proton decay. We don't need a beam, and Trident we need a beam. So yeah, so new physics search is one of the place. And another place is, solar neutrino physics. And if there is a supernova burst, we can do, really exciting physics for supernova burst.
Very good. Any last quick questions? We're getting close to the top of the hour. I think with that, we will wrap things up. But just to segue off of the supernova neutrinos comment you had, I'm personally very interested in seeing that signal. The neutrinos are already on their way. We would love to have DUNE online in early 2030 to catch those and tell us a whole lot more about how that explosion works. Alrighty, let's wrap things up. A reminder that today's talk will be available to view and share on institute.surf/JBC, YouTube and Vimeo. Next month's John McCall Colloquium will be on June 10th at 9 a.m. Mountain. The topic, Quantum Frontiers in Particle Physics, from sensing rare decays to solving collider challenges, with featured speaker Dr. Casey Kung. As a reminder, please join us on Slack right after this talk to continue the conversation with Dr. So and others. The link is in the chat. Finally, we value your feedback. Please take a moment to complete a short survey you'll receive in Zoom or by email. Your suggestions on future speakers and topics help ensure that this series remains relevant and useful to the community. Thank you all for joining us today. We hope that you'll join us again.